Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on rotating frame of reference. See, we have looked at expression for velocity. Just to emphasize that we are dealing with rotating frame of reference, I am showing this frame of reference rotating, and I have angular velocity as well as angular acceleration. We do not put any restriction on the rotating frame of reference. It can have velocity as well as acceleration. And in this animation, I have not said anything about point A. It could be viewed in many perspectives. Okay. One perspective was, I had shown that this is part of a rigid body with a slot and the point A is moving in a slot. Okay. We also saw other class of problems where I had this axis rotating like this. I am also going to discuss these problems today, fine. Certain aspects I am going to discuss about it. And I have the point A, which is looked from a rotating frame of reference. I have a position vector r, and this is r A with respect to B, and I have the position vector r A, and for this I have an expression for velocity written down like this, and the symbols A and B have specific meaning. B is the coordinate of the rotating frame of reference. Okay, that is the way we have labeled it, and A is the point of interest. And if I have different points in the problem, you should be able to rewrite this expression appropriately. And what is it that we have said about this? It can also be looked at as velocity of A with respect to the fixed frame xy equal to velocity of B plus omega cross r plus BA with respect to xy, small xy, and that is what is VREL. See, you take the advantage of a rotating frame of reference essentially to get VA small xy or AA small xy. That is the reason why you are looking for a rotating frame of reference. In fact, the first two problems I have solved, they require that knowledge, and it is easy to perceive if you have a rotating frame of reference. We will also have a look at it again. And this could be rewritten in this fashion. I can look at this as r dot xy, and this is what I have said, that the position vector is r. And I can also rewrite this as VA with respect to capital XY, VB with respect to capital XY, and R dot with respect to XY. From this we also get the knowledge that R dot capital XY equal to R dot small xy plus omega cross r. So, what we discussed was, when I sit in the rotating frame of reference, it is easier for me to measure R dot small xy. And the rotating frame, a person moving with the rotating frame misses the quantity omega cross r. And this is what generalized when we put this as any vector dv by dt in the fixed frame of reference equal to dv by dt xy plus omega cross v. In fact, we utilize this very systematically when we differentiated the velocity expression to get the acceleration. We use this repeatedly. This is very important. It is nothing but, if you look at this expression, this can be viewed in this fashion. Okay. So, that you have to be very clear about it, and we use this important expression from a fixed frame of reference to the rotating frame of reference. We utilized it for the derivation of acceleration. So, I have this VA, I can write it like this, and I can also note that r dot x y, I am again rewriting this r dot capital X y equal to r dot small x y plus omega cross r. This is to emphasize the fact. And I can also write this expression as V A equal to V B plus V A with respect to B. V A with respect to B has two terms. Do not write this V rel as V A with respect to B. Some students have done it. That is not the quantity. You perceive that velocity when you sit in a rotating frame of reference and move with it. But when I say the relative velocity expression, this V A with respect to B has two terms now, omega cross r plus V A x y. And when you use this expression very carefully for differentiating this, I get the expression for acceleration as like this. I have a V rel as well as A rel. This is a symbolism used in Merriam. So, I do not want to confuse you, so that I retain that same symbolism, and which can also be viewed as V A with respect to x y, small x y, A A with respect to small x y. And I said this is known as Coriolis acceleration. This was difficult to perceive if you sit in a rotating frame of reference and try to find out the quantity. And we will also have a detailed discussion about this in one of the classes later. And here again I can write acceleration A as acceleration B plus acceleration of A with respect to B. The acceleration of A with respect to B now has so many terms, 4 terms you have. So, what we have learnt is our ultimate objective is to get the absolute acceleration and absolute velocity, and we use the rotating frame of reference as an intermediary to do all the computations. It actually simplifies your analysis of a physical problem. Okay. And let us look at the problems that we seen in the last class. So, I had a problem like this. I had the fixed axis attached to this, and I had the rotating axis attached to this, and I deliberately gave the problem that the disk itself is rotating because the V rel is easier to compute from circular motion. But the students, what they had the confusion was, you have to recognize that this axis is rotating with angular velocity omega 1, this axis, fine. And once I stand on point B, I would perceive that this is rotating in a clockwise fashion. And look at, I have a point A marked, the point A is moving. So, this is the way that you will have to understand the relative, not the relative velocity, the velocity from a rotating frame of reference you can easily calculate based on circular motion. In this case, the object is rotating in a circle. While we developed the theory, we took a rigid body with a slot where the point A is moving within a slot. That is more complicated motion. Here the motion is far simpler, you do not need any new equations, the equations you already know, fine. Let us also look at it from a different perspective. Now, what I am going to do is, I am going to look at the side view of it. How do I make this appliance? I can think of this disk D is rotated by a motor with some gearbox so that I can adjust the speed, fine. And if I want to have another rotating platform on top of it, I can imagine that I have another small motor which rotates this. Is the idea clear? And I have the fixed axis here, and I have a rotating axis here, x, y and z, and this is rotating with an angular velocity omega 2. And now look at the picture. I have shown the picture as if this is stationary. only this is rotating. See, when you construct it, you have a motor, you have a speed reducer, and then you determine the speed that you can easily measure. You can easily measure that. So, in my rotating frame of reference, I use quantities that are measurable, fine. And then what I am actually saying is, when I have the point B, which is the origin of the frame of reference, you can imagine that there is a person sitting or standing at that point and view what happens. When she views it, she will only see that this object is rotating, because it is rotating with an angular velocity omega 2. Now it is very clear, fine, there is no difficulty at all. What I have shown here is, I have shown that this is static and this alone is rotating. Now what you will have to visualize is, suppose I also rotate this, but I still stand there, even then I would see the same rotation, I would not see anything else. See, you may say that I am too tall, so that I see what happens in this disk, what happens in the other disk. I can also shrink it, because these are all visualization. You do not see anything outside this blue disk, okay. You see only this disk, you will still perceive this disk is rotating. Is the idea clear? You have to get this idea, that is the reason why we use rotating frame of reference. See, here I do not have the path of point A from an absolute sense. From a way the mechanism is constructed, I can determine this velocity. Even when this disk is rotating at omega 1, this will still have omega 2 with respect to that. So, I use quantities that are easily determinable and then use it in my rotating frame of reference. That is why you use rotating, not for the heck of it you are using rotating frame of reference. Certain quantities are not possible for you to measure otherwise. So, we had first two problems like this. First problem is like this, where I have this and I use the quantities that are easy for you to measure. And even in this problem, only the rotation direction is different, it is rotating like this, okay, it is rotating like this. And here again, this axis has a rotation of this angular velocity, okay. We will solve other problems, make a neat sketch of this. And you have such gadgets available even in India now. If you want to replace any one of these fittings, you have such motions available in the truck, and the problem is like this. You have a multi-utility truck, it is useful to repair overhead fixtures is shown. At the instant shown, the truck is stationary and the base D is rotating at an angular speed omega 2. I have labeled the different part of this here. This is the base D. I have an arm here. I have labeled this as A, I have labeled this as B, and I have a platform attached at C. And the platform is such, it is self-aligning. Whenever the arm is having a motion like this, it will self-align itself, so that the person standing here will remain horizontal and he is in a position to do the job. And what is shown here is the rotating axis have both velocity as well as acceleration, both the cases. And this is rotating with angular velocity omega 2, and this is rotating with angular acceleration omega 2 dot, and here this arm is pinned here, and this is rotating with angular velocity omega 1. This is also have an angular acceleration of omega 1 dot. And here I have deliberately modified the symbols, so that you also get to know how to write the expression you have learnt in the class and how you convert it for the problem concern. Straightforward application of the equations that you have learned. There is nothing new here, but you have to be systematic. You have to do the calculation systematically. Fine. So, the first issue here is how do I determine the fixed axis, how do I determine the rotating axis, and where do I fit them. So, you are given this alpha is at 60 degrees and beta equal to 30 degrees. You are asked to find out the velocity and acceleration vectors of point B, it is put as pint, it is point B relative to the ground, and you are given this length of the member as dA equal to 12 meters and this length as 2.5 meters. So, you have to decide where do I put the fixed frame of reference and rotating frame of reference. You know, I have the point D, this is rotating about this. So, it is easier for me to put the fixed frame of reference to the truck. So, I will put the axis like this, I have xy axis like this, and we have already seen from the problem statement that this arm is having an angular velocity about point A. So, it is better to have a rotating frame of reference attached to point A, because I can easily calculate the value of the velocity of point B from the parameters given in the problem. That is the way you look at it, fine. So, it is easier for me to fix this xyz to point A, and with this choice, you know, I have no confusion of capital J and capital I and small j, they are parallel. So, I have no difficulty in handling the expression, because I already said when I say VA equal to VB plus omega cross R plus VREL, they are all referred to different coordinate system in a generic problem. So, you have to use the vectors properly, fine, and here no such confusion is there, but the only confusion is what we used it as point A has become point B, what we used it as point B has become point A. So, you have to know how to write this expression, and the motion is easy to visualize, there is no difficulty at all. See, ultimately in many instances you again invoke only circular motion equations in different forms. Circular motion equations are very useful. Here again, because this is rotating like this, I will again use that kind of expression for me to find out what is the velocity of B. So, these are all the quantities given, you are given the alpha and beta, omega 1 dot, omega 2 and omega 2 dot are given. So, let us determine the quantities. You have the position vector. So, this is nothing but 2.5 cos bi minus sin bj. So, when you substitute the quantities and simplify, I get this expression. R is turning out to be 2.16 I minus 1.25 j. Fairly simple and straightforward. See, one thumb rule is how do you select the rotating frame of reference? From the rotating frame of reference, I should be in a position to find out the velocity of the point of interest comfortably. That is the basis for you to select the rotating frame of reference. And when I put this coordinate axis like this, I can also find out the coordinate acceleration and velocity based on the other part of the problem. So, you identify the rotating frame of reference, where to fix it. That is the very important step in solving these problems. You should select the fixed frame of reference and rotating frame of reference carefully. Do not rush doing that. In friction problems, I said you should determine what is the direction of frictional force, otherwise you are solving a different problem altogether. So, in these problems, if you select the coordinate axis properly, rest of it is just application of the formula. While deriving the formula, we have looked at the physics, but for applying it, you do not need anything of that sort. You should do the calculation systematically. The motion of point B with respect to the rotating frame of reference can be found easily. That is the basis why you select the rotating frame of reference at this point. And from the problem statement, it has a rotation with respect to A. So, I have this as omega 1 cross r, fairly straightforward, and you are given omega 1, that is 0.3 k into the position vector. So, when I do this, I get the velocity with respect to the rotating frame of reference as 0.65 j plus 0.375 I meters per second. I have calculated VREL, I will also calculate AREL, because in my calculations I need VREL and AREL, that is all I need. Rest of it I need to have the quantities that is specified in the problem. AREL is also, you can easily do it because it is a circular motion. And what I will have, because I have omega 1 dot as well as omega 1, I have two components for the acceleration. So, you have a tangential acceleration as well as normal acceleration. In the previous problems, we did not have omega 1 dot, we had only the angular velocity, angular acceleration was 0. That is the kind of problems we have done earlier. So, it is fairly straightforward. You have to be careful in substituting the values properly and then do the computation. And here what is done, I have directly put the velocity, then I can put this as omega 1 cross v. So, it simplifies my calculations. So, I get the acceleration with respect to the rotating frame of reference as 1.305 I plus 2.7 j meters per second square. So, it is fairly straightforward. So, I have these two quantities. Now, I should apply my basic equations properly. So, there is no harm you write the expression what way you have learnt it in the class, but rewrite this expression specific to the problem of interest, because A and B positions are interchanged. So, I would now rewrite this as I have to get velocity of B with respect to capital XYZ and replace this term as coordinate velocity. That is a better way of understanding it. So, I am really looking at the coordinate velocity. Then I have omega cross r, and this omega is nothing but what is the angular velocity of the rotating frame. So, do not confuse this with omega 1. The rotating frame of reference has only omega 2 as the, it is rotating like this, it is rotating like this. That is where students have not understood what, when I give problems which has rotary motion, you get confused which rotary motion you are talking about. Now, omega 2 is this. So, I should write this, then rest of it is fairly straightforward, there is no difficulty at all. You are much better in doing these calculations than me. So, understand the concepts and get the quantities for this expression. So, coordinate velocity is nothing but I have this at a distance 12 meters. So, omega 2 cross dA, and dA is given from the problem statement like this, it is turning out to be 6I plus 10.392 J. Please verify these calculations. If there are any typographical errors, please bring it to my attention. And I have omega 2 cross dA minus 1.2 k meters per second, and you know it is a good practice to write the quantities like this, and it is also easier for us to check your answers in a large class of students. If you write them in steps, at least we would be in a better position to give you partial marks. So, have this habit of writing down these terms one after the other. So, omega 2 cross r is like this, and VREL is 0.65J plus 0.375I. And so, I have all the quantities for me to calculate VB. So, I get VB as 0.375I plus 0.65J minus 1.63K meters per second. See, what you will have to keep in mind is, I have chosen this rotating frame of reference because I can easily compute VREL. That is one of the bases that gives you a clue how to select a rotating frame of reference and where would I fix its origin, how will I put the axis. All that decision you can do by computing VREL and AREL. Am I in a position to compute VREL, AREL comfortably? So, we have calculated the velocity, then we move on to acceleration. Here again I write the expression as learnt in the class. This is not the expression that is to be used directly, we have to interchange the symbols and also substitute what is omega dot, omega and so on. We have already calculated VREL as well as AREL, and this omega is nothing but the rotating frame of reference, that is omega 2, and this will be omega 2 dot. So, here again I can write this as the point of interest is B, xyz equal to coordinate acceleration, AB I will write it as coordinate acceleration, plus omega 2 dot cross r plus omega 2 cross r 2 omega 2 cross VREL plus AREL. Here again simply substitute the values, you get the final expression. So, the coordinate acceleration is omega 2 dot cross dA plus omega 2 cross dA, and that turns out to be simplified to minus 2.4 k minus 0.24 I meters per second square. See, when I have coordinate acceleration, you have one more extra term, the computations become little longer, but the methodology still remains the same. You can easily comprehend the whole thing, but it is involved and you have to be alert and do your computation systematically. And here again, I follow this practice, individual terms I write, so that you can also verify them when you want to check your answers. And I have not simplified them, I have finally obtained the acceleration as 0.98 I plus 2.7 J minus 3.41 K meter per second square. It is again a straightforward problem. The idea is you are not using the same symbols in this problem, that is one difference, and the coordinates had, in addition to angular velocity, they also had acceleration. The idea of solving a variety of problem is, if you solve a variety of more number of problems, you also get to know how to attack a new problem which you have not done earlier. Fine. We will also solve another interesting problem which we have already seen in connection with the coincident points. You have a shaper mechanism, you can very clearly see the forward motion is slow and the backward motion is fast. So, while cutting the specimen, it goes slowly, when it comes out fast, and this is the mechanism that we are going to analyze. This is the mechanism that you have, and I also said lubrication is very, very important, and say actually in a bath of lubricating oil. So, we have already written down this problem earlier. Here we are interested in finding out the angular acceleration of link OC. For the angular velocity is phi radian, determine the velocity of point C for the instant when theta equal to 30 degree. If the angular acceleration of the crank is 10 radians per second, determine the angular acceleration of link OC. So, you have asked to find out both velocity and acceleration. And one of the aspects is, when problems are given in a book, they leave many things for your imagination. See, the position theta could be during the motion of the point where the block is moving from bottom to top, or it is coming from top to bottom. It could be either way. But when we have an animation, we have an understanding what is that we are looking at it. Okay. So, I have this, and this shows very well that you have a quick return. So, we are going to analyze a situation where the block is sliding from bottom to top and it has reached the position theta, because the problem can be interpreted in either way. Either it should be stated in the problem statement that the motion is like this, and then you are asked to find out, because the final answers would be different if I am analyzing a motion of the block coming down or going up. Is the idea clear? So, these are all the ambiguities that you have in a textbook problem. When I do the animation, at least I am in a position to say that I have come down, I have gone up. I am trying to analyze the problem when it has moved up. That is the way I am going to look at it. And whenever I have a slotted member, the thumb rule is you attach the rotating frame of reference to the slotted member, because in a slotted member the path of the particle is known. It may be easier to calculate, it may be difficult to calculate, at least the path is known. In this case, this is simply sliding in this. So, I am going to have a linear velocity here, okay, and this member is having an angular motion like this. So, that is the way your rotating frame of reference, okay, it is oscillating actually. In this case it is, but anyway we are going to analyze it only for a particular position of the crank position. So, in all these problems you have to decide what is the fixed axis and the rotating axis. So, fix the axis at point O and then have the axis aligned to the member. You have small x and small y along the slotted member and perpendicular to that. Then you have to calculate some of these quantities using geometry. So, I can find out ROB as 396.61 millimeter, and here what you have is, I have the axis like this, but the rotating axis they are not aligned. So, you have to be careful in handling the capital I and capital J and small I and small j. So, instead what I will do is, I will find out everything with respect to xy, small xy. So, we need to get certain other quantities. So, I get the angle beta as 13.9 degrees. So, you have to bring in your sine rule, property of triangles. For solving a problem you need that as well. It would be convenient to use the rotating frame of reference for expressing all vectors. So, I should have some discipline, because when you have that expression, this is referred with respect to different axes. If they are collinear or parallel or coincident, then there is no difficulty. If they are inclined, then you have to be very careful in handling your vectors. So, I will have RAB, okay, this is referred with respect to I and j, small I and small j. So, I get this as 110 cos 46.1 I minus 110 sin 46.1 j millimeters. So, that is reduced to this quantity. And I have the basic expression. In fact, I have written down for this specific problem. So, we are interested in finding out the velocity of B, that is equal to VO plus omega OC. OC is this member, because that is the angular velocity of the rotating frame cross ROB plus VREL. And because point O is fixed, the velocity of O is 0. Okay. So, if you graduate, then you can directly write the expression appropriate to the problem. Whichever way you do it, I have no difficulty. Okay. You can write what is the expression taught in the class and then convert that to the first specific problem of interest. And write each one of these quantities. VB is nothing but omega AB cross RAB. You should recognize that this is part of the crank. So, I get the absolute velocity directly. So, here the left hand side is known. I do not know what is the angular velocity. That is what I am supposed to calculate from this. And then your VREL is nothing but x dot I. So, this is the convenience. If I attach the rotating frame of reference, then the VREL is very simple to write. It is nothing but x dot I. And substituting in equation 1. So, I put this equating the terms in x and y direction. I get x dot as T 96.3 millimeters per second, omega OC as 0.9615 radians per second, and we are asked to find out what is the velocity of point C. So, from circular motion I can write this as omega cross ROC. So, that turns out to be 528.83 millimeter per second. Fairly straightforward. You have to be careful in selecting the fixed frame of reference and rotating frame of reference. Then apply the equations systematically, handle the vectors properly. So, now I have to find out the acceleration, that is also written for this specific problem. And here again you will have A naught is 0 because it is a fixed point. And we have to get AB, it has omega dot AB cross RAB plus omega AB cross omega AB cross RAB. And you have the expression for this. And you have been able to calculate this. So, I have this Coriolis component. Can you just find out what is the direction of this? The direction of Coriolis component is this. Please make a sketch and note this. And you find this perpendicular to the slot. We will discuss about it a little while later. You will always find this is perpendicular to the slot when I have a slotted member. The sense is determined by the angular velocity. And one of the important aspect in Coriolis acceleration, what is the direction of Coriolis acceleration? This is one of the important parameters that you need to find out. And then I have ARL as x double dot I. So, I can group the I terms and j terms, and you can determine the quantities that are required to be found. So, substituting in equation 2, I get this, equating the I and j components. I get x double dot equal to minus 748.63 millimeter per second squared, and omega naught c as the angular acceleration is 5 radians per second squared. And we have already seen that omega naught c is 0.9615 radians per second, and Vc is also summarized. So, it is again a straightforward problem. You have a satisfaction that whatever that the mechanism that is used in a shaper, which is a important machining operation in the machine shop, and you know how to handle it from your knowledge of rotating frame of reference. In fact, when we discussed the coincident point, I took this for you to appreciate what is the velocity, fine. And in all these problems, what you find, this problem is slightly different. I do not know the ARL and VREL. I determine ARL and VREL by solving the problem, but I know very well that a slotted member, this member can have only a linear motion like this. I use that as a basis to select the rotating frame of reference. See, in the earlier problems, you are able to calculate ARL and VRL comfortably. Here, I do not know how to compute them initially, but I know how these quantities are. Fine. So, the problem could be coined on any one, the left hand side is known or right hand side is known. So, you can equate the two and then find out the rest. So, in this class we have reviewed how we determine the velocity and acceleration when I have a rotating frame of reference. A person sitting on a rotating frame, he will be able to find out VRL and ARL comfortably, but he misses out omega cross R, in a generic fashion omega cross V, and that is used when you want to differentiate the velocity expression to get the acceleration systematically. And once you finally get this, the expression can be written down as VA equal to VB plus VA with respect to B and AA equal to AB plus AA with respect to B. These relative quantities can have more number of terms depending on whether you are finding out the velocity or the acceleration. And we also reviewed the two problems we have done earlier, so that you get a clarity what is happening to the rotating frame of reference, what is that you perceive. And in all the problems, I said that the challenge is how to identify the rotating frame of reference and how to identify the fixed frame of reference. So, for determining this, please pay attention, take your time to fix them. Then rest of the problem is straightforward, mere application of the formula with careful attention on the mathematics, because this is written down in different frame of reference. So, the capital I, capital J, small I, small j, you have to handle it properly. We have not looked at any problem where it is too complicated, they are all very simple as of now. You can also have problems where these are little involved, there you do not make a mistake. So, handle the vector equations properly. Thank you.